welcome to another edition of the Finite element seminar at LLNL. This is a hybrid version. We haven't got one of those in a while. Speaker is here in person. Svetlana Tokareva from LLNL. It's our pleasure to have her. Thank you all for coming. And thank you also for all the people that have joined us online. Let me introduce Svetlana. Getting her for a long time. She's another high-order Lagrangian person. She did her PhD at ETH, then did a postdoc at the University of Zurich with MF-FEM. And it has been in LLNL for 7-8 years. She staffed there, has a lot of exciting projects, and she's going to tell us about how they work. On the side, she's also a famous instructor in Santa Fe, so if you need high-order help or skill learning help, Svetlana is a person. Thanks for coming, of course. Oh, by the way, we have room to meet with her. She's here today and tomorrow, so if anything you hear today is interesting, you want to follow up, please let me and Vladimir know and we'll arrange a meeting. And so with that, Svetlana, thank you for coming.
Thank you, Sanio. It's my pleasure to be here and see everybody in person, and thank you for inviting me to the seminar. All right, so today I will tell you about our research on high-order matrix-free finite elements for hyperbolic problems. And how do I switch this? Okay. Right, so first of all, I would like to acknowledge all of my collaborators from LLNL, Stephen Walton, Eric Tober, and my current postdocs. We have people from Texas A&M. I even put another one twice there. I don't know why, but extra credit to another. Sorry. Yes, and of course my Remy Graf, who was my mentor as a postdoc at the University of Zurich, and Daniel Morgan, who's a long-term collaborator at LLNL. Right, so here's the outline of my talk. I will present my approach to matrix-free finite elements, mass matrix-free finite elements, which combines the residual distribution, discretization in space, and the deferred correction type stepping. Then I will show you some applications of this method to Lagrangian hydro, which are of interest to many of you. And then I'll talk about enforcing some structure-preserving properties in our ID of method, and if I have time, I'll talk about Advection-diffusion problems. Okay, so let's start with this matrix-free FEM framework. So we will consider a hyperbolic PDE, which is the vector at the top of this slide. So du dt plus nabla f. U is a vector of conserved variables. F are some hyperbolic fluxes. And as we all very well know, we start by introducing a polynomial interpolation in space, like this. UIs here are high degrees of freedom, and these phi polynomials are by basis functions. Right, so, and as we know, typically a finite element method would lead to some kind of ODE with f on the right-hand side. U mold is the vector of all this degree of freedom, and M is some global sparse mass matrix, right? So you would normally have to introduce a linear solver to obtain these coefficients at every time step, or every sub-time step if you're doing higher order time integration. So the matrix-free methodology in my notation doesn't have this matrix M, and instead we have a diagonal mass matrix. So when I say matrix-free, this is what I mean. My mass matrix is diagonal, so if there is no mass matrix, there is nothing to invert, no linear solvers need to be involved. So this idea is different from other matrix-free notations that other people use. So for example, partial assembly is something different. So I'm trying to construct a high-order finite elements with diagonal mass matrix. All right, so let me briefly introduce that ID residual distribution concept in space. So it's best to do it first for a steady state problem, so forget the time derivative for a moment. And so a residual distribution framework consists of 3 steps at high level. So first we introduce the quantity that we call phi k, that we'll call it a residual or fluctuation, and that is simply the integral of the nabla f term over the element. So here the element is some kind of polygon, doesn't have to be, just for the illustration purposes. So at the second step, this total fluctuation or residual phi k will be split between the degrees of freedom in the element k. And this is done typically by introducing some distribution coefficients beta and multiplying the total residual with this distribution coefficients. And now at the final step, we'll look at degree of freedom I, and we gather all the residuals from the elements that are sharing this degree of freedom. And this gives me the resulting scheme with respect to the unknown degrees of freedom. All right, so in practice, at the first step, we introduce also the so-called stabilized residual. So this quantity phi I k alpha is nothing but the Lagrangian residual, Lagrangian projection, with some added artificial viscosity. And this artificial viscosity in the RDA scheme can be something very simple, first order. What we need from that is that consolation property, so the sum of VIK coefficients in the element must be equal to 0, which is needed for conservation. And so instead of computing this quantity directly, we first introduced stabilized residuals, and then the sum of the stabilized residual will give me that total residual. So these VIK alpha residuals are used to compute the distribution coefficients beta ik at the second step. All right, so like I said, the viscosity model for our residuals can be something very simple. So often we use something like this Lars-Friedrichs or Rusanov type viscosity with alpha some viscosity coefficient. That is the estimate on the largest eigenvalue of the flux Jacobian, and ui is the degree of freedom, and u bar here is the average of u in the element. So to compute the distribution coefficients themselves, the betas, we have normally typically used this relation that was introduced in Pyro and Abgral in their earlier work, and later I will discuss alternative definitions that utilize the invariant numerical reservation to compute the betas. All right, so so that was a steady state case. Now let's look at time dependent problems. So for time dependent problems, we can define functionals L, which essentially are PDE residuals. So this is simply a space-time projection of the PDE onto my approximation space, so that will be an L2 projection in space-time. And so what we could do to discretize one, we could write an honest high-order approximation with high-order polynomials in space and something high-order in time, and we would have to retain that mass matrix Mij, which is that global sparse mass matrix. So that would be my high-order approximation. But I could also lump the mass matrix, so diagonalize that M by, for example, summing the columns or the rows and just writing that coefficient on the diagonal. And that would give me a low order approximation. Now these operators IH and IL here are some interpolators in time, because we have that integral within the density. So that is kind of the basic high-level idea here. So we have two different approximations on the same PDE. And so there is a useful lemma that tells us that we could combine those two discretizations in the iterative process here. So the to compute the iterative high-order solution, which is denoted by Y here. So there are some requirements on the operators, the low L and LH. So L has to be coercive with some C1 constant, and the difference has to be Lipschitz. And then we have a convergence result here. So in practice, for high order in time, what we do is we look at the time step Tn, Tn plus 1, and we introduce sub time steps. So within Tn, Tn plus 1, we also introduce m sub steps. They could be equispaced or they could follow some Chebyshev points or something like that. So we introduce the solutions U, N, M at each one of these time steps. And we define the iterative time stepping method, which will be of deferred correction type, as follows. So we evaluate operator, low order operator at iteration r plus 1 for each one of these subtime steps. And on the right hand side, we have the difference between low order and high order at the iteration r. So for the low order operator, we want to make it explicit. High order operator can be anything. The resulting time step method will be explicit with respect to this new iteration, and also high order. And you can find the proofs in earlier papers by Remy Abrel, for example. All right, so this is what the low order operator looks like for practical computations. So here, the first term, so first of all, it's a vector, right, defined for every degree of freedom, sigma. So for at each time level within that time step, Tn, Tn plus 1, we have a different integral of the residual interpolated in time. So this is the second term that approximates the number f, essentially. The first term simply approximates the time derivative. Now here what's important is instead of the mass matrix, I have that lumped mass coefficient sigma. All right, and so to make that operator explicit in time, instead of interpolating between the Tn and Tn plus 1 time step, I simply take the residual at u Tn. That's what it is. Now, in the high order operator, we keep the consistent mass matrix, and we introduce a higher order polynomial interpolator between Tn and Tn plus 1, and then again we compute the integrals slightly differently for different stage. So, yes, and IH will be the interpolating polynomial of degree m in time of my residuals. And so then we combine these two operators, and the resulting high order RD scale will look as follows. So because we had low order operator on the left hand side and on the right hand side, what comes out is this difference between the two iterations. But to evaluate that r plus 1 solution, we don't have to worry about the mass matrix, because all you have here is that one coefficient on the diagonal. And so what changes in the RD framework is that now in the residual itself, you do have the contribution from the time derivative, but again, this will be evaluated at the previous iteration, so there is nothing to invert nonlinears over here. So that terms in red is what can be used on as my caloric residual, and these coefficients will be used to compute total residuals according to that first table that I presented, and then to compute the beta coefficients. So that is the final scheme. Now I wanted to say, yes, a few more things about this beta I coefficients, the distribution. So the definition that we have been using until recently was based on the 2003 paper by Abrel and Rowe. And those coefficients were defined for good reasons on triangular elements in 2D. And so what we found is that this definition seems to generalize, and it works okay in 2D for Q1 to Q1, so you can use that exact same formula. The drawback we found is that for really high order elements, like anything above like second order, in time-dependent problems, you do lose some accuracy. And so in part 3 of my talk, I will focus on just rethinking the meaning of these coefficients using convex limiting for higher problems.
Svetlana, just clarification, when you say Q1, Q2, this means
linear quadratic
geometry.
Yeah.
Also.
Yeah. On boards. Yeah. All right. So in 2018, we had a paper where we have shown that this residual distribution with deferred correction in time, matrix-free converges for smooth problems in the related formulation. Yeah, and that was the big result. All right, so now let me show you the applications of that method to Lagrangian hydro methods. And again, I would like to give credits here to Stephen and Nathaniel. Stephen did most of the hard work there in this project, the coding and computations. All right, so Lagrangian hydro. Here we have the order equations that are written in the moving reference frame. Right, so we have the model consists of three equations. So conservation laws for mass, momentum, and total energy. These are the specific energy. Right, we write them with respect to density, velocity, and internal energy. And the model has to be complemented by the equation of motion. So we need to know how to move our control points. Yeah, and so our finite element discretization follows very closely the work of Sanyo and Rob and Veselin. So we also use what they call staggered grids. And we have different approximation spaces for the velocity and for thermodynamics. So velocity and mesh applications will be approximated using continuous finite elements. So it's an H1 space, and I have the basis functions phi. So we do have continuity across elements. For thermodynamic space, we don't require continuity, so that is closer to a discontinuous Gaussian idea. So on every element, you still have a polynomial approximation for the energy, but that polynomial space is 1 degree lower than the kinematic one. All right, so this is the finite element. And so we apply that same residual distribution with deferred correction idea. So all these one and two operators can be defined for each one of the equations separately. So we solve momentum and we solve the specific internal energy equation. Density will be computed using strong mass conservation. So we don't actually have a PDE for density. We just use the Lagrangian transformation Jacobians to recompute the density. But everything else is the same. So we define those operators that are introduced before, and we apply them separately to every equation, including the equation of motion, because that's an ODE. And the resulting scheme, I have it here for second order. So when we want second order in time, we only need to do 2 iterations. So for k equals 0 and 1, yeah, that's what we update. And again, you can see that we have in the velocity equation, we have that lumped mass on the right hand side. So instead of linear solve, I just have to divide by that mass coefficient. And the same for the energy equation, even though the energy space is discontinuous. So if we decided to keep the full mass matrix, that would be log diagonal, which of course helps, but we could also lump it. It's kind of optional. We didn't observe a huge difference between the results whether we lump the matrix or not in the energy equation. So I'm just throwing it out there.
Then some.
Yeah.
What is n in the last equation?
And
N. Yeah.
oh, it just denotes the time step. So from Tn, and that's the time iteration.
Cool. And what is k?
And k is the so it's this second order is essentially a predictor corrector scheme. So first I update with k equals 0, which gives me the predictor step, and then with k equals 1
Is xn plus 1.
will be yeah.
And can you guarantee exact energy conservation, total energy conservation with this?
That's a great question. No, you cannot in general. So this is why these terms, the correction terms, epsilon and epsilon k are here. And so I'm not going to talk about energy correction here, but you can derive the correction terms for the energy equation. But yeah, in general not, but that's it's kind of a price to pay. I did this before. Suffix. Yeah. So in the Lagrangian hydro, we add artificial viscosity to our stress tensor. So this is a little bit different from the classical RD framework that adds just some viscosity or stabilization terms to the residuals directly. So here we modify the stress tensor, and so we add the sigma A coefficient, which is the artificial stress tensor. And there is nothing new as here. So the sigma A has the form of mu epsilon, where epsilon is the symmetric gradient and mu is some viscosity coefficient. And so I guess what is maybe slightly different here from our previous work we've done is that we now use this sigmoidal limiter to activate the viscosity only where needed. So it does depend on some compression ratio, and so we want to make sure that this mu is as close to 0 as possible where the solution is smooth, but it does get activated when shocks. And so this model function looks like that with some tunable parameter A. If again, yeah, so that is our viscosity model, but I didn't want to focus too much on that. Like I said, this is pretty typical and standard. All right, so here are some results. So of course,
sorry.
Okay, you
You're
still
going
want
fast. Are there any if statements in your work to show viscosity?
any?
If statements? Or is
So
it
the
also-
reason for using that sigmoidal limiter is to not have if statement.
So there's no.
Yeah, so it's smooth. I mean, there are some parameters, right? So A is technically you want to adjust the width of that sigmoidal function.
At the length scale, is it
One scale is
similar to what we do?
yeah, it's very high. It's I think it's even the same. Yeah. Right. No, we did not like the method with if statements.
Understood?
Yeah, lots of switches and stuff. All right, so we looked at all the typical test problems for Lagrangian hydro. So tailor-made vortex. This result you see here. This is a 16 by 16 mesh, and this uses Q4 and Q3 elements. So polynomials, cubic polynomials in the energy, and then degree 4 polynomials in the velocity space. So the result at t equals 0.5 shown here. You can see that. So in this test, what we want to see is the stationary velocity field, and we have very smooth mass deformation, and the velocity looks pretty close to the initial. So it looks like a great result. And we could run this simulation till about 1.5 or so. It still does really robust mass deformation. Well, the next test case set off, again, we're using Q4, Q3 simulation in 3D, so everything runs in 3D now. So we have the scatter plots for the density. On the left, it's a pretty coarse mesh, 8 by 8 by 8. On the right, slightly finer mesh, 16 by 16. And we reach almost the analogic maximum peak. And of course, so in this test case, actually we didn't run with any energy correction, but because it's pretty accurate, you don't, I mean, yes, you lose some conservation, but visually at least it still looks pretty good. We could have added those energy correction terms. Yeah. It becomes more important lower orders, high orders. All right, so triple point. Again, the simulation is in 3D. I'm just showing the 2D projection. So Q4, Q3 elements on the bottom compared to Q1, Q0 elements at the top. So the total number of nodes that we had to use to achieve a similar quality of the triple point, the vortex. I mean, clearly the high order elements, which I don't have to use when I'm using high order elements, because we need a lot less. We need a much coarser mesh for high order elements. Yeah, and so once again, I don't have any linear solvers. My math matrices are absolutely non-existent. They're gone. So this is just a zoom of that triple point at t equals 5. So the only problem with this simulation was actually visualizing a high order mesh in front of you. For some reason, there is a problem. We're working on it. Hopefully, we'll resolve the. So you see the straight segments, but this is actually just degrees of freedom in the mesh connected by straight. Anyway.
Do you have the ability to plot more than the cell average?
Ability to plot?
Well, you're plotting one number per cell.
Yeah. Because this is density. Density was because density is element-wise anyway. So we plot the cell average. But let's say for that velocity that I was showing, failing. So this is velocity field, and we want every degree of freedom. So that will be.
Use PowerView. Does PowerView natively support higher than it? We have a slide.
No, we just export the program.
So do you
We try
subdivide in many points to show the count?
Yeah, I think you can do it for continuous fields, but for discontinuous, you have to break the mesh into like individual elements.
Yeah.
And treat each as a continuous element. For the discontinuous things like so they'll
Yeah, so that's the reason why I plot the cell average is because it was just too wild. Too much work. We care about seeing that mesh makes funny brain. All right. So any questions?
I have a question.
Yeah.
I'm sorry, I missed like the first bit of your talk, but have you shown scaling results?
Scaling?
Yeah.
We have. I don't have it here in this talk, but my collaborators have some scaling result for this method. The code we're using is it's called Fiero, and that's not Nathaniel Morgan is the main developer on the Fiero code. It won R&D 100 award this year, so it scales pretty well. I mean, we're still working on scaling for really high order elements, but to get lower order for scaling, it scales well on GPUs.
Yeah. So like, since we're removing the linear solves, I assume that when you go weak scale, it looks really good. Like, is it pretty flat?
Yeah. And it helps not having the metrics remerge. Everything's that old,
I just maybe you said I may have missed it. Did you say the time integrator that which order you're using for that for like the higher orders? Are you using a fourth order integrator to mean time?
No. So we don't do method of lines here. That's the main difference. Is we use some iterative time stepping.
Right. So so it's defined by how many iterations you take.
So for second order, it takes 2 iterations.
Mm-hmm.
So that would be in terms of iterations, that is equivalent to Rugekura fine order.
Mm-hmm.
Except instead of discretizing the right-hand side first in space and solving using the method of lines, we discretize space-time residuals, and then we use this iterative process, which I had earlier.
Right. I just put for comparison with those.
So combining some lower and higher operators using this and doing the iterations.
Yes. Then the results were done with the 2 iteration version.
Yeah. So we have a second order right now. These results were so second order in time because why not try for the convergence studies? Yes, we did higher order than second, but for like just to run these kind of problems, second order is what we find, kind of good compromise in terms of accuracy and computational cost.
So you use second order in time even when it's Q4.
Yeah. I mean, we could do high. It's just because the results still look good. I mean, increasing the order in space seems to have a bigger impact than just doing 5%. I think. That's the only reason. I feel. All right. So I can maybe move on to my next topic, and that is.
May I ask one other
Oh, yes,
question?
sure.
I'm sorry to do that, but that for the time stepping, the time step size, how do you choose your time step?
Time step size, so Tn plus 1.
Yeah.
That size, it's just a normal CFL. Condition. Or there in CFL.
Okay.
It's explicit.
Yeah, I know. Just but also for the high order. Okay. Oh, you divide the length scale by p, right? Yeah. Okay. No, yeah.
This it's just a normal CFL.
Element by element. Yeah, that's it. Yeah.
All right. Okay, so the one part that was missing for a long time in this our matrix-free finite element scheme was enforcing the structure preservation, say at the mathematical fundamental level. And so what we have done recently is, like I mentioned before, we tried to rethink the distribution coefficients, and we tried to enforce these structure preservation properties or invariant domain preservation by controlling those beta IK coefficients. So structure preserving scheme, what you would want normally is, of course, conservation, positivity, let's say density, everything has to be positive, local bounds. Maybe you want to embed also entropy inequality, maybe some asymptotics, equilibrium solutions, things like that. So here we follow the ideas where we were inspired by work of Kuzmin and Germont and other people on structure preserving methods, and the basic idea is still the same. So IDP framework, right, invariant domain preserving, which is the same as notation as structure preserving. So the basic idea is to construct a low order method with provable properties, right? So something low order, not very accurate, but provably positive, let's say. And then you might want a higher order version of that scheme with that violates the IDP property. And then we can blend the low order and high order schemes and do some kind of convex limiting of that blended scheme. And here what I will show is the connection of the convex limiter with the distribution coefficients for the RT framework. So for the low order scheme, so what I have on the slide is the graph artificial viscosity low order scheme that is was used by Germont and others. It doesn't have to be exactly that, it's just for the demonstration purposes. So scheme 7 is something low order that you know has satisfied those RDP constraints. And so here, Mi again is the lumped mass, right? And Ui is the low order solution, and so f of uj is include the flux evaluated at the degree of freedom j. So this is a global version of that. That's right. Finite element scheme. Anyway, so it turns out that this scheme can be very easily written in terms of residual distribution, right? So we don't change the scheme, we just write it differently. So if we, so we're trying here to extract the stabilized residuals from equation 7. So the residual distribution scheme, we want it to look like the sum over all elements containing degree of freedom I, beta ik, low order, phi k. Phi k will be the total residual. And so beta ik, as we know, they are computed, they can be computed as the ratio between phi k nodal and phi k total. And so these nodal residuals can be defined from equation 7 as given here at the bottom of this slide. So it's just a local version of equation 7. And everything else can be computed. All right, so for the high order scheme, I can write something very similar, except I want different distribution coefficients that are called beta ikh for high order, but that still looks almost the same. So the difference is in which beta coefficients we're using, high order or low order. And now, as it's always done, we compute the difference between this high order scheme 9 and the previous low order scheme, which gives me the following convex combination with the positive coefficient. So mi here is the lumped mass around the node I, and mik is the contribution from the element j to that same node I. But everything else,
Just close.
okay. Right, so this is the convex sum, right? And so the idea is that if every term in that convex sum is IDP, if it's in that invariant domain set, then the high order solution also will be. So we want to compute this beta ikh in a way that the IDP property is preserved. And so what is
Here.
Yep, that's exactly what I said. So what we found is that if we define that beta ikh, so high order beta, is blending, so it's a blended high order beta that we take from the just purely Galerkin scheme, that is unstabilized FEM, just high order FEM, Galerkin. And beta ikl is that low order scheme that we computed from the low order IDP method. Yeah, all we need to do is introduce this blending parameter, theta k, and if theta k equals 1, then you will get back your high order purely Galerkin finite elements, and then if theta equals 0, then you'll get your low order scheme. So the ideal scheme is somewhere in between theta k. And so with this definition, we can substitute 11 into my convex sum, this better beta kh. And what comes out is interesting, because what comes out is that this blended parameter is exactly the ITP limiter. So the way, if you look at Germon's work and Dimitri's work, so they all introduce limiter somewhere in the this right hand side, and so we can follow exactly the techniques that have been introduced before to compute that theta, and so Jean-Luc does it using convex, so ITP limiting, right? So the lemma here that's guarantees that convex limiting is if you have functional psi of u, so if that functional is positive on every let's say every term, every u plus this sigma k pk on the right hand side, so if that is positive for every one of these terms, then it will be positive for also uih. All right, so that's the basic idea, and then one could follow the method of lines to find that optimal theta. For certain properties, such as local bounds, you don't even need any method of line search, so we can analytically derive the best possible theta k. So if I know what my local bounds should be, ui minimum, ui maximum, I can make my ITP functional positive by setting that sigma k to something that I can compute another plane, which is very good. And so we try to, right, so once I know that theta, I can define my high order distribution coefficient, just like this, and then I can do my RD with deferred correction or anything like that. So yeah, and we have applied, for now, these are just 1D Eulerian results, but we're working on extending that to 3D Eulerian and Lagrangian. So yeah, in these plots, you see blue is the low order scaling, so same with Lux physics viscosity. Beta RD green is the one that uses a kind of common beta definition, and then the purple one is the new IPRD scheme. And you can see that you get a much better representation, much better resolution of aftershocks. For solid, then of course show washer, you get a much better resolution in the oscillations area, which these oscillations are physical. This is not something spurious. This is what we wanted. The exact solution will be pretty much on top of this purple lines. And we looked at Numerical, so interaction of really strong shocks. Again, we have a much better resolution just by introducing local bounds. There is here that we only have local bounds on the solution. Right. Yeah. And so I don't know. Should we maybe save time for questions? Because well,
It's up to you. We get plenty.
yeah. Well, I can just show. So we are working also on Advection-diffusion problems as an extension of everything that's been done before. And here we're trying to combine that deferred correction matrix free for the advection step with something implicit for the diffusion step. And so typically what we're trying to do is introduce that multi-rate time integration, where the diffusion component, the slow component here, we'll use something, an implicit scheme. And for the advection, the fast component of the ODE, we will use the same DAG matrix we found. And so we will work with Adrian Sandu on this. So we use essentially his MRI guard methods. The difference is that we use the DAG matrix for the explicit part of the equation. So we save a little bit of time, and again, I don't have to worry about linear solve in this part, but of course there is still some solver that you need for diffusion. There is nothing that you can do about that. So yeah, the results look promising, but it's still very much a work in progress still. So yeah, and like I said, we did this RD. We developed the RD framework for higher schemes. Different hyperbolic PDEs. They are matrix free. There is no, in the sense that mass matrix is diagonal. It extends pretty easily to higher order space and time. IDP property can, now we have an understanding of how to enforce it by means of the distribution coefficients and convex limiting. Work in progress is what we will introduce more IDP properties such as entropy inequalities and things like that. Extension of IDP to 2D, 3D, and the Lagrangian matrix free FEM IDPRDs working properties. Yeah, I think I'll stop here. Thank you, everyone.
Right, thank you. Applause here. Okay, questions for Svetlana.
Could you go back to, I guess, section 3 when you were defining the bounds for your IDP method? I think I missed D. So with what defines this neighborhood? Is it
So we use the low order scheme with guaranteed IDP properties to define the local bounds. So if we compute the solution,
and what's the neighborhood over which you're?
That's a good question. So I'm looking at the degrees of freedom in the element.
Just the element. not any no element neighbors?
There must be neighbors.
There are neighbors, so elements around the degree of freedom. So it will be the stencil.
Was base
Yeah.
stencil, or could it be like the full?
So the elements that talk to the degree of freedom.
Okay, yeah.
Is that in your case, is that talking through faces or through vertices?
Vertices.
Good.
So you look at the stencil that it defines.
And then, sorry, I missed another question. In the definition of the is, I think it might have been the next slide. Yeah.
In the IDP
Yeah.
version, so the definition is it's this equation 11 where so betas is a blended sum or a convex sum of beta I k g, which is just Galerkin beta. So you take the Galerkin scheme, no viscosity, no stabilization, nothing, just high order that in principle will be unstable and violating all kinds of IDP properties. And the second one will be the lower scheme. And then you try to find that beta, which is a convex linear, turns out, and then you compute the blended, which, so interestingly, that equation 11 is, many years ago, Remy, in our previous work, we realized that with Remy that you can blend higher and lower schemes, but we tried to have some sort of a priori estimate on that theta. But then turns out that we just didn't know enough about convex limiting. That's
So
a better approach.
that bounds preserving low order scheme, does that depend on the physics? Like, are there limitations to that? Like, or does it assume an ideal gas equation state, or is there some entropy?
Well, lower scheme will depend on the physics because this artificial viscosity will be different based on physics. So, in principle, yes, it depends on the physics.
Okay.
Can I quick follow up on 11?
Yeah.
Isn't 11 just a convex combination of the Galerkin and the low resolution? You put that.
It is a convex combination of Galerkin and lower resolution. So once you compute the thetas, we could compute the residuals directly without like bypassing the beta step.
I mean, isn't 11 equivalent to taking the same theta gate combination of U, UG, and UL?
I don't think so.
No?
We didn't page cards.
Okay, other
It's equivalent
questions?
to taking the combination of the residuals. Like I said, you can bypass the beta step for some reason. I think
Okay.
Dmitry there has a question.
Yeah, if folks who might have a question, we can see. So please unmute and just ask the questions.
Yeah, so I have another remark regarding 11. So in the scalar case, it's just an element-based FCT algorithm, like the one we used in the paper with Sanyo and Rob and others in and Manuel in 2015. And also the closed, so if you are imposing local bounds on a scalar quantity, that's again a scalar element-based FCT algorithm. And in our experience, it was not enough to use like one element-based correction factor. So in 11, it seems that there is one theta per element. And we found such algorithms to be very diffusive because if you violate constraints in one node, you basically punish all other nodes of the element. Yes, and so I'm wondering which quantity, in the context of Lagrangian hydro, what is U? Is it density? Or do you have several quantities? Because this is not quite convex limiting. It's like an old FCT type limiter. So what is U?
Well, so this was for the other equations. U is density, velocity, and total energy. So we applied that limiter on like each equation.
But
Okay, so You're using this for individual conserved variables or for
Yeah, yeah.
individual variables.
So you would be the vector of conserved variables.
Yes, yes. But then how do you, okay, you're evolving internal energy. So in this way, you enforce
Without evolve,
negativity of the internal energy.
without evolve internal energy, in this one it's Eulerian, right? So I'm solving still
Okay.
the density, momentum, and total energy.
Yeah, yeah, but then you don't have a non-negativity of the internal energy, do you? So there's no way, if you're using an Eulerian schema, there's no way to limit the internal energy directly because it's not one of the quantities that you're evolving, which means that you need to limit a momentum and total energy in such a way that non-negativity constraints hold for the internal energy. So limiting conserved quantities individually does not guarantee positivity preservation for the internal energy, and therefore it does not guarantee preservation of invariant domains.
So, like I said, we only looked at local bounds here for each of the U components. So the
Yes.
positivity of internal energy is not something I looked at. It was not a problem for this kind of tests.
Mm.
We didn't see it here.
Wouldn't you see it in the equation on state if it is staggered?
Yeah, it would, you know, basically my code would crash.
Yeah.
It got negative, but it didn't. So,
Okay.
I mean, it's a great remark, Benjamin. Like I said, we're still.
Okay, thank you. Well, I just noticed that in our experience, limiting individual quantities, individual conserved quantities is not enough because if you limit like density, momentum, and total energy, you easily get oscillations in the velocity and pressure fields. Yes, and these oscillations then create oscillations in other fields. So there are some ways to improve this. For example, Reinhold Lune, you might know his work on element-based FCT. So what they do, for example, they calculate correction factors for different quantities of interest, and they take the minimum. Yes, yeah, but I guess it would be incorrect to call this invariant domain preserving, but because an invariant domain of the Euler system is a set of quantities that have non-negative internal energy. And this can also be enforced using in your approach. Yeah, but then the constraints, so you cannot impose a local bounds on the internal energy directly. You need to limit conserved variables using like a line search, as you mentioned. We present such an algorithm in my paper with Khrushchev, which I mentioned to you in Breckenridge.
Yeah.
So if you need, anyway, if you need a limiter for internal energy, we can discuss this later. Our experience.
Very interesting.
Thank you, Dmitry. There's a question from Elias who couldn't unmute. It's about the relation to some TGSM work of Jasper by Ramirez. Are you familiar with this?
I think I've seen. Well, I've seen a few papers on TGSM. Well, this is not DG. What we do is not necessarily DG. So we have continuous continuous fields for what I presented for Lagrangian hydro. Also with Eulerian results that will have been computed with continuous finite element. So that is, I guess, the main difference. I know that DGSM results in the diagonalized matrix by construction because the collocated exists, but it's a different scheme.
Yeah. Thank you. Other questions?
I have a question. So if you don't need to do linear solves, what's the dominant cause of your study?
It's a good question. I'd say, well, computing the residuals is where we spend time. So, you know, computing this approximation of the advection operator, now by F.
So what's just to clarify this, what's the complexity of this with respect to the order?
The order?
Yeah. Or with respect to the question of O1 for degree of freedom is O_P for degree of freedom? So Cij, for example, in your previous slide, is this an actual quantity that you compute?
I don't compute Cij, it's just the scheme has not the way they present. So,
Well, do you compute any matrix-like quantity, or is it all vectors?
So there is still matrix, like the mass matrix is there if the space-time residual. So we have to compute it, but we don't have to solve a system with that matrix. That is our and we could do something better to save computational costs. So this is the matrix quantities got. I mean, the computing the quadrature is really expensive. That's, I guess, the computational cost here. To approximate this residual step would be high answer on this.
You didn't talk about it, but what is the finite element basis in the spaces that you're using? Because mass matrices in some bases, as you know, can get zero diagonals.
Right, so it's actually a good question. Yeah, so we could always use just positive Bernstein basis, because that would guarantee that my masses are positive. But for in 2D for quads, right, and for hex in 3D, we found that Lagrangian still gives you just a normal Lagrangian features. Doesn't give you the
uniform degrees of freedom or Gaussian bottom?
we do the Gaussian enough.
Yeah.
Yeah, one thing in Bernstein is very inaccurate.
Inaccurate in what sense?
You just do the lumping. The lumping depends on the basis, right? So if you do it in Bernstein basis, it's a very good approximation.
We did try Bernstein. I would say it's a very bad and inaccurate approximation. I didn't see it as very bad. It's actually less, well, I guess it might be a bit more diffusive than Lagrange, but it also leads to
I think that's what.
less, better. I actually see a smoother mesh with Bernstein. So I don't know, like accuracy is, I guess it's personal choice.
So
I didn't have a horrible experience with Bernstein.
this method does depend on the basis, though, right? Because lumping depends on the basis.
You will get, in principle, a different lump mass at different bases, because all you do is...
And then different results.
Yep.
Fundamentally, mathematically, they are different, yes.
Okay. Questions?
Yeah. I had some with this case. Could you go to the Eulerian solid chalk cube results you had again? And I just wanted to understand.
Eulerian?
Yeah, it looked like you had the different ways of computing the residual distribution factors.
Okay, if that's...
Yeah, I wanted to understand. So, it looked like your IDP method was a lot less diffusive, and as opposed to the, I'm guessing, the previous way.
Yeah.
Beta. So, to what do you attribute that improvement? What's the difference between those two methods that's largely accounting for that?
Well, so what this blending does for me is, you kind of shift the distribution step closer to the high order scheme.
Okay.
But we still make sure that you stay within the bounds.
So
Whereas the previous definition, it knows nothing about local bounds. We just want to. So the way these betas were defined many years ago, 1 year ago, it's just so. Okay, I can talk about it a little bit. So what originally was done is they tried to interpret these beta coefficients from the low order scheme as some barycentric coordinates in the triangle. And then if you have the new beta, it goes outside of the triangle and you try to project it back. And that's essentially what that formula, the max with max things, that's what it does, right? We penalize some high order scheme by reprojecting it back into the triangle in some sense. So it would find when there are 3 beta coefficients, because that gives you the barycentric coordinates, and you can interpret them like this. And like I said, we did, well, of course, the first thing to try when we went on to quads and hexes is to try the same thing. It did work, not so well for high orders, okay for, let's say, linear elements and quadratic elements. So, yeah, that's, I think, the main reason is because this formula knows nothing about local bounds or any kind of other constraints.
Just to clarify, this in the higher order case for higher order element, these beta coefficients, they do depend implicitly on the Jacobian, the element transformations, right? They're not topological.
So the Jacobian will be hidden.
But for the same, if you have the same element but with different geometry, you will have different betas.
Yeah, addition. Yes. It does. It does depend on the Jacobian because the Jacobian is sitting here when we compute the right hand side, and that will be used.
Makes sense. You showed this in a kind of very general case for polygons, and in
We
practice.
are working on extending this in polygons.
But in practice, you've done triangles and hexes so far. Is that right?
Many years ago, yes, it started on as you know, they started with triangles. Then we started doing quads and hexes because in Lagrangian, I work mostly in the Lagrangian methods, and quads are just better than triangles there. So
Can you run triangles?
I can run triangles.
Do you get similarly looking results?
You get reasonably looking results, but not as much.
But our experience that
Yeah.